Hello, everyone. This is Volts for January 9th, 2026, believe it or not. What's the deal with closed-loop geothermal? I'm your host, David Roberts. Way back in 2020, I wrote an article for Vox that I am told served as many people's introduction to geothermal energy, just before the latest hype cycle really got going. I went through all the levels. There is conventional geothermal, in which water is injected into rock fractured by existing volcanic or tectonic activity. There's enhanced geothermal, like Fervo, in which water is injected into deliberately engineered fractures in the rock. And then, a little further out on the tech development horizon, there's advanced geothermal, which includes all sorts of wacky stuff, like what's going on over at Quaise, a company doing geothermal with lasers. Microwaves. One of the advanced technologies I cited in that original piece and have been keeping a close eye on since is closed-loop geothermal, which is exactly what it sounds like. A system in which the injected water is confined to sealed pipes rather than filtering out into the hot rock. It's effectively like building a giant, extremely deep underground radiator. The company trying to pull this off is called Eavor, E-A-V-O-R. I told them years ago that when they built an actual plant and began producing actual heat and power for sale, I would have them on the show. Well, they just flipped the switch on a plant in Germany, which will eventually put 8.2 megawatts of electricity on the regional grid and 64 megawatts of heat into local district heating systems. And I am a man of my word, so with me today I have Jeanine Vany, co-founder and executive vice president, and Mark Fitzgerald, the newly minted, as of a couple of months ago, CEO of Eavor, to discuss the technology, the business case, and the promise of closed-loop geothermal. With no further ado, Jeanine Vany, Mark Fitzgerald, welcome to Volts. Thank you so much for coming.
Thank you for having me.
Yeah, thank you so much, David. It's great to be here, especially after we flip the switch, as you talked about.
It's nice to have that in the rearview mirror, I bet.
Yeah.
So, Mark, I have got a bunch of questions about the business case here and the way you intend to sort of ladder this up. But I want to, if you will indulge me, I want to start with Jeanine, and I want to just get a little nerdy up front about this technology. I want to explore a little bit about the nuts and bolts of this technology. So, Jeanine, this plant in Germany, let me describe. So there is an injection well. It goes down 2.8 miles, very far, unusually far. Goes down 2.8 miles, takes a 90-degree turn, and then starts going laterally, splits into 4 tubes. Those 4 tubes go out laterally 1.8 miles, and then loop back on themselves, return back to the origin point, re-merge, and then come back up as an output well next to the injection well. I think that's an accurate description thus far. I have many questions about this. And one of them, it might be the goofiest question, but it just occurred to me, and I'm very curious about it. You're going out 1.8 miles laterally from your drilling site. Do you have to own all that land? Do you have to own the land on top of the lateral wells, or is there some legal arrangement where you're allowed to dig deep enough under people's land? How does that work? It's hardly the most essential thing here, but I'm just curious.
It's a great question, but I just want to zoom out again and say, when you told me that we could come on the podcast after we were commercial, challenge accepted, and you were my source of inspiration, Dave.
Oh yeah,
over the
I was
last
getting
2
on
years.
volts that pulled
Getting
you
on
across.
volts. Yes. So thank you again for having us on. So that the question on the land, it's a question we commonly get. And you need to own the surface footprint, typically where you're building your plant on it. And then you lease what's called mineral rights for the zone that you want to produce out of. So no, you do not have to own the surface under where you're drilling. And that's pretty common in a lot of places.
Yeah, yeah. And so my basic question here, I really think this is the fundamental question, engineering wise, technically wise. So the disadvantage, like one of the things conventional geothermal does is it squirts the water down into the ground, and then the water then sort of fans out, it leaks out into the rock, meaning it creates a wide surface area in which it can absorb heat. Your water or your fluid, which we'll get back to, your fluid is contained, sealed in these pipes, which means it's got much less surface area to contact hot rock. This is the basic disadvantage. And so all of the sort of engineering choices that are made, I think, are to compensate for that. One thing is you go a lot deeper, so you find rock that's a lot hotter, and then you move your water a lot longer of a distance through that rock than conventional geothermal. Is that basically right? So I guess what I'm asking is, that seems like a substantial disadvantage. You must think there are compensatory advantages. So why do this? Why deny yourself all that surface area? What are you getting out of keeping the water in a tube?
So I think what you're ultimately referring to, and so for hydrothermal, remember, you are sourcing water from an aquifer. So there's rocks that have pores or spaces in it that hold water that you ultimately pump to the surface. And so you inject water down just to have some flow in the reservoir, and then you have to pump it out. So just remember the pumping piece, because pumping is very important. So then if we get to sort of the mode of extracting energy in either EGS or in the hydrothermal systems is a convection-based model, which typically does have, you can produce more megawatts with less wells. On our side, we have a conductive heat transfer method, which does mean in order to contact enough surface area, we build out these loops that you mostly described correctly. So that we compensate for the convective heat flow by drilling this large set of lateral wells. And you're absolutely right. There is a reason we're doing that. And we think there are many, many upsides to doing that. And one of them is the siting flexibility that we have. So we're not restricted to looking for hot rock close to the surface. So even in the fracking methodology, you still need to find hot rock to flow the fluid through. Our whole value proposition and premise is to make this technology available anywhere in average geothermal gradients. So that is one of the fundamental things that we are trying to achieve.
Yeah, I was going to ask this later, but let's get to it now. So as you say, part of what you boast here is that you're geography agnostic. And a lot of people, like I threw this out on social media, and a lot of people came back with the same question, which is, there's agnostic and there's agnostic. How geography agnostic are we talking about? Literally anywhere, or are there some restrictions?
There are, of course, always going to be restrictions because you're not probably going to want to drill on the top of a volcano or in a critically stressed area. And I would also add, we probably don't want to drill where successful hydrothermal reservoirs are because they already have a successful reservoir. So typically what we're looking for is a good regulatory framework, an area that has the demand, and relatively boring geology. And I think that's something that a lot of folks don't realize is hydrothermal reservoirs, you're looking for faults in active areas and you're trying to suck the water out because it's naturally flowing up these fault zones, right?
Right.
So you're actively seeking out that type of geology. In EGS, you're seeking just hot rock. For us, we're not seeking those things. We're seeking to be in very stable areas with no faults, so we have no risks of induced seismicity at all. And I think also very important, I think, to talk about is that siting flexibility. Once we rule out any sort of geohazards, we have a high, I think, social license to operate because we don't use a lot of water. Most of our system is built underground. So when we're producing the water, it's not really producing, but we inject down the inlet well and it goes around and comes back up the outlet well. Most of that infrastructure is built under the ground. And because we're not producing large volumes of water from the underground, we have nothing to treat. So we have no scaling or corrosion issues. We have no future operating expenses, which is not something that people talk about enough. So we have high capital expenses up front where we have to drill and build this radiator. We've been very forthcoming that 80% of our costs, our capital cost, is just the drilling. So you dial that in, you've built an asset that just operates for 100 years, no re-drilling, no water.
Well, this is important. Let's talk about the water. So one of the obvious advantages of closed loop is that you pump the water down and all the water comes back up because it never leaks out into the, and again, there's all, and then there's all, like presumably there's some
No.
leakage.
I'll tell you the leakage. It's been proven. So I think it's really important to know that we have built and operated a pilot plant in Canada for 5 years. And it's a good thing we did because we have a lot of history to point to. So what we had was a leak off, which translated to like 2 cubic meters a day, which is like a garden hose leaking. If you want to have zero leak off, you can inject and pump down more of our rock pipe sealant. But we have really like 5 years of data that we show we have almost no leak off whatsoever.
So truly negligible, meaning the amount of water you start with is more or less you're good. You have a finite amount of water, and that's all you're basically ever going to need. You're not going to need to bring in more water. Okay, that's super interesting. One of the big questions I had as I was thinking about this, so first of all, you're building the injection well and what is the name for the other well, the output?
We call it the inlet. So we don't really inject into the formation. So we call it an inlet well and an outlet well.
Okay, the inlet well and the outlet well are going down 2.8 miles, and then you're turning, and each one of these loops, we mentioned that the pipe splits into 4, and each of those 4 loops, it goes out and comes back, gathering heat. Like it goes out and comes back, and the pipe, as it goes out and comes back, needs to be a stable distance from itself and from the other lateral pipes.
Yeah.
In other words, you're doing fairly high precision drilling 2.8 miles underground, where I am assuming like radio signals and Wi-Fi, like there's no way to communicate with the drills from the surface. So they must be smart somehow. How are you doing this? What is it? Talk to us about the drilling technology itself, because I saw that you had been using off-the-shelf technology and have recently transitioned to using your own bespoke drill. So tell me a little bit about the drill itself.
Sure. Would it be okay just to correct the description of the technology for your listeners?
Please.
So we do drill vertically down, like 2 wells side by side on the same surface pad or same surface area. And once we get to the temperature we want, we'll turn right and we'll drill out. And we drill 12 wells on each pad for each horizontal, and then we connect them toe to toe with magnetic ranging, and that closes the loop. And then once we close the loop, we seal the loop, and then we fill the loop up with water. Then we have a little small pump on surface. Well, we truck the water in, fill it up. It's about the size of an Olympic swimming pool. I don't have the gallons in my mind right now, apologies. But once we start it up, we turn that pump off, and it operates under a thermosiphon. So the density driven differences from just the cold water and the warm water coming out.
Right. I was going to touch on this later, but I want to emphasize this because it's slightly mind-blowing. So all you have to do is just drop the water down the pipe, and the temperature differentials underground do the pumping for you. So you're not pumping water down or pumping it back up. It is doing that on its own.
You are correct. So we do want to be clear, like we do have a small pump on surface that we start it with because it needs something to push it down. But then, as I mentioned, the water heats up and then it wants to rise. And so it is called a thermosiphon effect. And what we just demonstrated in Germany is that we only need 1 degree of temper differential, and this thing just goes on its own. So we are completely black start capable. So we are, if the lights turn off or there's some kind of like tornado or hurricane, if there's some kind of military issue, it's a very bunkered, reliable, secure energy resource that stays producing. Even if you can't power a pump, it stays producing. And I think that's a huge advantage.
So you don't need ongoing electricity, basically. Like once
No.
it's going, and you need no further additional electricity to keep it going.
That's very true. So I know I didn't answer your question about connecting wells downhole.
Well, you mentioned connecting them at the toe
Yeah.
with magnetic something, but like how's that working?
Okay, so when we first started the company, and even my own experience drilling, like I am a geologist, I spent 15 years working oil and gas before starting this company. We all know of this thing called an ellipse of uncertainty, which means when you're drilling, you sort of know where you are, but the bit can drift a little bit in this sort of azimuthal or east-west direction.
And I'm correct, right, that you can't directly communicate with it.
No, you can.
You can.
You can. So I'll get to that. So a lot of people said, you'll never, ever connect these wells. And of course, I had never connected wells before either as a geologist, but I started researching this thing called magnetic ranging, and it's actually an anti-collision technology that oil and gas producers use so they don't collide wells, right? So we just like turned it on its head and took an anti-collision technology to collide wells. And we did it the first try in Alberta at like a mile underground. And now we've done it in Germany at 3 miles underground. And we're connecting 6.5-inch well bores that deep. And so it is an amazing level of precision. And so how we do that is there's a spinning magnet, and it spins and it emits a rare earth element. And then there's a magnet on the other side. And so it's picking it up. And so you just do like you drill a few meters, and then you do what's called a check shot. And then you'll look at the math, and there'll be like an ellipse of a bunch of different points. And then your directional guys will reorient you, and then you'll march another 10 meters until you sort of connect. So that technology is what's called wireline conveyed. So, it does take time for the data like to come back up the wireline and things like that, but you can communicate to the surface.
There's a wire. You're communicating via a wire in the...
We call it a wireline tool. So Mark is an engineer by training, and he came up through oil and gas and led a lot of the unconventional development. So I'm not the only person who can speak on the technology. So I'll kick it to Mark if you want to add something about
Mark,
our
anything
AMR
to add
tool?
on how you connect two 6-inch wells that are, wait, let me do the math, like almost 4 miles away from you?
Yeah, and you know what, David? They're actually going to be even longer as we continue to innovate and develop, right? And I have to say, I was quite enjoying listening to this podcast you and Jeanine were doing. So,
Okay.
yeah, but I think it's fantastic what Eavor has been able to create here. And, probably the simplest way for listeners to think is, as you've described it, at the end of a long wire is a tool that knows exactly where the other tool is. They talk to each other and they say, I'm this distance away in this direction. And then you just continue to bring them together. And it's a little more complicated than that. But I think for simplicity, think of a tool at the end of the wire that says, here I am, here I am. And another one at the end of the wire on another well says, here I am. And then they just go meet each other.
You can just say magnets.
Thank you.
You say magnets. I'm going to throw the word magnets at it.
Magnets.
Yeah.
That's the best way.
I would say that our team took that technology and then elevated it even more to our own active magnetic ranging tool. And so you might say, okay, why is it active? And so Mark was talking about like the older style of conveying it through wireline. We can now connect this on the bottom of the bottom hole assembly
While drilling.
So normally you have to drill, and then you have to pull all of your tools out. So that's 2.5 miles. That takes a long time.
Right.
And then go back in. So what we figured out how to do is to finish drilling, and then this tool that's sitting on the bottom hole assembly allows you just to switch into ranging mode. And so it's processing all the information downhole now instead of having to send a signal back.
So wait, you used to have to pull your rig out, do the check, put the rig back in, and go 10 more meters? That must have taken forever prior to this.
Well, you didn't have to pull the tool out, but you did have to wait to interpret the data longer. But to start the tool, yes, you had to pull it out and go back in. So we shaved off a lot of time.
So they're communicating as they go.
Yep.
Now.
Yeah.
Okay. So when we say closed loop, the vertical wells, as I understand it, the inlet and the outlet are actual tubes. Yes? Plastic tubes?
I think I know what you're saying. So how we drill these wells is similar to anyone else drilling a well. We drill it with the same drill pipe and the same tools, and then we case it according to all of the environmental regulatory standards. So we cement casing in there. It's called a casing string. And then we turn the horizontal. And I think what you're getting at is what we do in the horizontal section that might be different.
Right. So basically waterproofing the vertical wells is standard operating procedure. Something that everybody does. Your innovation is, how do you waterproof lateral well? How do you?
So I would say, first of all, I think it's important for the audience, if you've got a geothermal audience, we have to case these wells for integrity reasons, to protect, so that there could be no accidents, or you're drilling through layers and layers and layers and layers of sediments, right? What if you drill through a hydrocarbon reservoir? Well, you don't want to produce it. So you set the well up and you seal everything off, and that is your level of protection, and that protects your operating scheme. So in the horizontal section, we create our own pseudo casing by pumping down an alkali silicate mud. So we pump it down and it sets into the pore space of the rock and it hardens. And then we pressure test it up and we make sure that we have an effective seal. And that then acts like a steel casing would. So that provides the stability of the wellbore, and it also provides the, as you would call it, waterproofing.
It's almost like grout.
Yeah, it's almost like grout. Absolutely.
It runs along the walls of these
pipes,
horizontal tubes,
yep,
sifts into them, and then hardens. And this waterproofing, again, this sealant, you're saying will hold up basically forever. Like, you don't need to go reseal.
You can reseal
2 or 3 years.
You can reseal, and the good thing about our technology is we could monitor it real time just using software. So if you start to see any sort of leak off, you can manage that by just trucking in and pumping down and resealing it. And we actually did that in Everlight. So we had, I forget the numbers, but in our technology pilot in Canada, we had, we'll say 3 cubic meters a day of leak off, and then we pumped down a sealant, and then we showed to have lower leak off. So we actually showed we can do intervention if required.
And this sealant, I mean, should people worry about it? Is there toxic stuff in there?
No, it's a great question. We get that a lot, and we've shared it. Obviously, we share it with the regulatory bodies as well, but it's nothing at all to worry about. It's silica and then a couple of other components.
And the fluid that you're pumping down, you say it's water-based. The actual fluid that's absorbing the heat, what is it?
It is fresh water. And then what we add to it is corrosion inhibitors and biocides. And we do that because we want to keep it clean. We don't want it to sort of foul or anything like that. But it is just fresh water, and we can truck it in.
Sort of looking ahead, is there any discussion of other fluids? Is that one of the areas of advance here? Or is water good enough?
We get this question a lot, and my engineers keep telling me, no, we're sticking with water. But I think
simple.
I think the reason for that, again, is social license to operate. If you want to start putting supercritical CO2 into your wells, you have a whole other, regulatory hurdle. And so when we're nascent and new and trying to scale up, we want to be able to move and be able to operate. And as we hone the technology and scale it up, well, okay, maybe we'll start considering ideas like that.
So the Germany plant, 2.8 miles down, 1.8 miles out. How far down do you eventually envision going, and how far out do you eventually envision going? And is there a ceiling on either of those numbers?
Well, in Germany, we're drilling a horizontal configuration, and that works very well for the heat market in sedimentary basins. The plan long-term for utility scale power production is most certainly to drill deeper, because as you drill deeper, you unlock much more thermal energy per meter drilled, right? And I listened to Quase's podcast. And
are you going to try to go down and get supercritical?
No. But he did a great job of explaining that denominator, right? To you, like, if we can attack that thermal energy, get more energy out of the ground, we can get a better, dollars per megawatt hour. So he already kind of primed you for that. And so that's exactly what we're looking to do as well. So in the case of an Everloop of more of a subvertical well construction profile, we would drill down to, like, standard oil and gas equipment. They have drilled down to 12 kilometers in, I believe, Russia was the deepest borehole. And it took, I think, years to do it. China just drilled another really, really deep hole using standard oil and gas technology. But it's not quick to do. And there are limitations. So right now, the thinking out there is somewhere around 8 kilometers is kind of where you're maxing out with the technology that's sort of off the shelf.
8 kilometers is
5 miles.
5
5
miles.
miles.
Parochial American audience here. Thank
Yeah.
you, Mark. 5 miles. So that's not a physical limitation. That's more of a practical, that's kind of the sweet spot, practically speaking.
Yeah, and it depends on your thermal gradient and, different regional considerations. And we won't be drilling, I said, laterally. So it's mostly almost straight down because that's what we want to do to get more heat.
Oh, well, where will the loops go?
So that you just build them, they look the same, but it, like Mark explains it really well, it almost looks like the tines of a fork.
So instead of the vertical well doing a 90-degree turn, it does like a
10.
Just keeps going.
45-degree turn, or?
Think of it more like an 80.
Yeah.
It's 10 degree or 80, however you look at it.
Oh, I see. So your loops are mostly extending down rather than out.
Yeah.
I mean, one of the things I wonder is, for a given set of vertical wells, how many of these horizontal branches can you do? There's 4 off the well in Germany, right?
No, Germany there's 4 different loops planned on the same pad, but one loop itself, on average, is 24 laterals. So 12 off each, and they connect to turn into 12. So that's where you're getting 4 from, is that we're planning to skid our rig over and drill another loop and skid the rig over and drill another loop and skid the rig over and drill one more.
So that will be 48 lateral
Yeah.
holes, all told, to do the 4 loops. So for a given set of vertical wells, how many of those loops could you do? Like, I mean, spatially, there's a lot of room down there.
Yeah.
Is there an upper limit?
No, it's quite scalable. That's one thing that's really interesting about the technology is we're starting with smaller, like some companies are starting with a 30 megawatt, is the sweet spot maybe for a plant. I think I heard Quays is saying they're around 30 megawatts. We're starting with about a 10 megawatt plant, but the goal is to be able to scale these up to be deploying hundreds of megawatts, if not gigawatts, in one area.
That's a lot of wells. A gigawatt would be a lot of wells. So this is 4 right now to produce the whatever it is, the 8-ish megawatts you're producing. That is with the 4
Correct.
laterals, 8 megawatts with 4 laterals. So laddering up to a gigawatt, you're getting into like dozens and dozens,
Yes.
possibly hundreds of laterals. How many of those can fit on a single vertical? Is there, I mean, I can imagine a vertical and then just like a Christmas tree of laterals branching off it. I don't know if there are practical limitations to.
There are. I think you can design it in many ways, but like the Garrett's Reed footprint is about, I don't know, is it acres or hectares that you like to talk in?
Acres are the parochial American version.
Yeah, so right now we have about an 8-acre footprint for the 8 megawatts electric. But again, if you're...
that's surface?
Surface.
Got it.
Yeah, surface. But like if you're going to do modularized systems, then the plant can scale. So you can build a power plant that could be a 30, 50, it's whatever your development field looks like. So you probably would start with either a 10 or a 30 megawatt plant, but then you would build it out over time. So you could envision a series of plants in one area with wells tied in, with several wells on a pad. So this is pretty normal in oil and gas or in geothermal. Your surface footprint is going to be much, much smaller for geothermal than, say, other incumbent renewable energy sources, because everything is sort of built under the ground. So you start to spread out under the ground a little bit, but the surface footprint is actually pretty tidy.
Yeah. And another question I got is, presumably you're looking for areas with low seismic activity, but like if there were seismic activity, presumably this sort of, it seems like this lattice work of tubes that are a precise distance from one another are pretty vulnerable, and it would be like an earthquake could tear it apart. Is that something you think about at all or worry about?
I think about it, but I don't know that it would tear it apart. And I guess it depends on also the epicenter of where the earthquake is coming from. Lots of wells have withstood earthquakes. And, many of even the next gen geothermal plants that are fracking, they publish their seismic activity on their website, right? And so their wells are withstanding their earthquakes that they're generating. So I think that the same method could be templated over to us.
I think like a couple of things. The drilling down deep and horizontally has been done for decades and decades across North America. And so to your point, the vulnerability of that to earthquakes or seismicity is very, very low. Like there's really never been but I mean, the counter to that is that the development that we do does not induce seismicity either. In other words, because we're not proceeding down, that changing the gradient or the pressure gradients and the mechanics, the geomechanics subsurface, we also don't create induced seismicity, which ensures that we don't have any risk of integrity in terms of our own development either, which I think is an important thing that we continue to focus on.
Another question I always get a ton is, for a given area that you've got lateral wells going through, is it possible to drain it, like exhaust the heat in some time frame? And if so, does the heat eventually regenerate? How does that all work? Like, is there a life cycle in those terms? Like, can you exhaust the heat in the earth in an area? Hey there, everybody. Don't worry, I'm not going to tell you about a new mattress or push a credit card on you. This isn't an ad. There are no ads on Volts. It is supported entirely by listeners like you. If you'll indulge me for a second, I'd like to ask for your support. I started Volts because we're all surrounded by depressing news about climate change and misinformation about clean energy, and it's never been more important to share the stories of the real people on the ground doing the real work of transition, and all the ingenuity and courage and public spirit they are bringing to it. People are hungry to hear these stories, to learn from and find inspiration in them. I've heard from people who changed majors or careers after hearing episodes of Volts, people using it in classrooms and community groups, even state legislators who have passed bills inspired by specific episodes. Sharing these stories matters. It makes a difference. If you have found value in it and want to help me continue doing it, I hope you will join the community of paid subscribers at volts.wtf. It's about the cost of a cup of coffee a month. If you don't like subscriptions, you can make a one-time contribution, leave a review on Apple or Spotify, or just tell a friend about Volts. I am grateful for any and all support. If you're already a paid subscriber, thank you. And now, back to the show. How does that all work? Like, is there a life cycle in those terms? Like, can you exhaust the heat in the earth in an area?
It's a great question, and it's a common question. So the key consideration is how you design your wells. So we have a fully coupled reservoir simulation, and all that means is you connect your wells, horizontal wells to your vertical to your plant, and there's an energy balance. And so we know what rate we have to flow the wells at. We know what spacing they need to be at, and we model this over a 100-year lifetime. So if you do not have prudent operation and you flow it too fast, you can cool it down. If you operate inside of your energy balance model, this should not decline for a period of, well, I'll explain it if you'll indulge me.
Sure, please.
This is a closed loop myth buster. I want to do a myth buster if I can. So that's a common question we get. And as much as we've done a lot of third-party work with NREL and others, National Lab of the Rockies.
Whatever the hell they're calling it now.
It remains a common misconception that we have this fast thermal decline. And so we operated for 5 years at Everlight in this technology demonstration project in Alberta, and I keep going back to it because we proved it there. You have a rate, and the rate of thermal energy starts to decline almost exponentially, and then at the 5-year mark, it flattens off, and it stays flat for 30 years. And then it declines 1% per year after that. So these truly are generational assets. And how do we know that? Is that we predicted this model in advance with our modeling, and then we drilled it and we produced it and we history matched it back. And we were within 2% of our predicted thermal output for 5 years. So we do have a very predictable resource here, but you have to operate it properly. You have to space your wells.
You have to confine yourself to a certain rate of extraction.
Absolutely.
Is that a meaningful constraint? You know what I mean? Does that put it puts a ceiling on the amount that a particular plant can produce at a particular time?
No, and maybe that isn't maybe the best way to explain it. I guess what I'm trying to say is, if you want this to be a generational asset, you operate it in a certain way and you design your wells for that. So in contrast to, say, different types of projects, like maybe the fracking projects, where you drill a set of wells, you inject water, there's a thermal front that moves through, and once that thermal front has hit the other well, you're done, and you have to redrill a new set of wells. So that is the difference. There's an overnight capital cost to build that system, and then there's this ongoing full field development planning costs that we, like this closed loop technology, just doesn't have. And I think that is really not well known.
And does it, like, say you built one of these and you told your buyer this will operate at full capacity factor for 30 years? That's what we're guaranteeing, 30 years. And then after 30 years, there's some meaningful decline. If you left it alone, would it reheat after
Yes, it would.
30 more years?
I think it would. Have I done the model? No, but I feel like it's another challenge, Dave. You've challenge accepted.
All right. Yeah, I want to see the first revived, like abandoned and then revived geothermal. Okay, Mark, I hope you have enjoyed this technical podcast that I invited you to be an audience.
I'm quite enjoying this. You two go ahead and keep going. Yeah, this is great.
Well, I want to ask you a few questions here, and you can both chip in on this. Obviously, there's this test plant, and then this Germany was sort of a pilot plant. I'm curious if you have any sense of the timeline that you can expect once you're out of pilot phase and you're commercial, from sort of like prospecting, finding the spot, assessing the spot, permitting, drills, et cetera, financing for pre-development. I'm just sort of curious how fast one of these things could go from zero to built, basically envisioning in, 5 years after you've operated for a while.
Yeah, of course. And I mean, you hit the nail on the head for us, right? As Jeanine talked about, the history of Eavor is concept, just this incredible creative mindset, tested in Northern Alberta, discovered it worked, tested it in Germany. And, I'm probably the luckiest CEO in the world because all I've done for 6 weeks since I've been here is go party to party to party and celebration to celebration
well,
to celebration.
Well, it's pretty hilarious.
Right?
I read the white paper about the Germany project, and there were troubles along the way. There were challenges. There were things that had to be overcome, and you sort of sailed in at the end of all that, right when they popped the cork.
It was all perfectly planned, right? I'll skip all the hard stuff, and I left that for Jeanine and the rest of them. But in any event, the milestone that we press released a couple of weeks ago is so material for the organization because we're able to say, as Jeanine highlighted, the thermal delivery from this system is as or better than expected. It works. We can spin the turbine. We've generated power as anticipated, and we've generated the heat as anticipated. So all those milestones or those concerns that were raised by people in terms of it's not going to work, it may not, all that's done. It's all done.
We know it can work.
We know it works.
It can work.
So going forward, there's two things for us, and you've highlighted them. One is, where do we commercialize this? Where is the next facility? Where's the next project? Where's the next Everloop?
Let's talk about that then. Like, I want to know how you plan to ladder up. Like right now, I'm guessing the electricity you're producing is expensive. And you're in Germany, you're sort of heavily subsidized. This plant, we've got a lot of grants, first of a kind type stuff. So this Germany plant is in sort of like the ideal spot. And you're going to have to branch out and ladder up from there. Yeah. So where is the first rung of the ladder, I guess, is my question.
Yeah, the first rung for us very much is the heat market.
Interesting. European specifically?
Absolutely. The European district heating model is one that's natural for us. I think many of your listeners in the US may not be fully cognizant of that, but essentially think of one big heat source, one big boiler driven from coal or natural gas or biomass or otherwise that then creates the heat that supplies a whole community. And part of the opportunity for us is for municipalities and regions in Europe that want to transition to a fully decarbonized, reliable, and efficient means of district heating. We're there, and we're already highly competitive in that market. And so that will be a strong focus for us.
Let me stop you there. The heat that you can produce today is financially competitive with other heat sources for district heating in Europe.
Absolutely.
So you could go build a plant tomorrow and be competitive in a district heating setting.
We could.
One other question about heat. How hot can you get? Because there's sort of this threshold, you up to like 100 C or whatever, you're mostly in district heating or sort of low temp industrial applications. And then there's sort of this like, 100 C threshold where if you get hot enough, you can start being used in more intensive industrial. How hot is what you produce?
So remember, in the German district heating market, we're drilling horizontally in sedimentary basins. And so you're typically going to be in, oh gosh, I need to convert from Celsius to Fahrenheit. Around
It's the worst
300,
one.
around 300 Fahrenheit, I think, is around 180 or 150 C Celsius. And so then when you're delivering that to the surface, you're probably at like 120 degrees Celsius, which is maybe 200
You do
Fahrenheit.
lose a few degrees in transit,
You lose a
presumably the
bit.
2.8 miles of transit upward.
You lose a bit, but my point is that we are not with these systems delivering what you could sort of decarbonize steel with. Like, we're delivering energy so that we can plug into, it's like plug and play, if I may, with coal fired or natural gas fired district heating plants. So very different from North America. There's thousands of district
Yeah.
heating systems, right? So we can just plug in our system. So I just wanted to make sure that you understood like that it's the reservoir limitation there. If we were to drill a deeper configuration, we could be looking at much higher temperatures. And I think that's around maybe 500, 600 Fahrenheit where we would top out.
Your tech is capable of going deep enough to produce water hot enough to serve in those industrial applications, theoretically.
Theoretically, yeah. And I think, David, your point you're after is a really, really important one. Forever, we have shown that it works. And now, where's the market? Where do we take the next step? And the next step is the district heating market in Europe, where we're already competitive. How do we do that? We are a technology company. The DNA and the expertise in Eavor is the innovation, the creativity, everything that you've allowed us to brag about here on the podcast is our DNA. There are companies across the world that are really good at executing, drilling and executing and building and developing. And so for us, it's creating those partnerships in these regions that say, we'll bring our expertise, we'll bring the Everloop geothermal systems, we'll bring the next evolution of that. You bring your expertise in drilling and facilities development and regional markets and otherwise. That is the model for us right now.
Interesting. So you're going to license yourself to project developers, basically, to begin with.
Yeah, and we talk a lot about, it'd be really fun to be a developer. It was a lot of fun to do Garrett's Reed. That's not who we are. Like, our expertise is in the development of the technology and the innovation. The next step is when we look around the world, as Jeanine talked about, as we go deeper and hotter, as we become more efficient, and my background's in unconventional resource development, I know how that learning curve works. We will get there. As we continue to innovate, then we are absolutely firm in our view that we will compete against wind and solar and modular reactors and LNG and otherwise to generate power.
So you're saying that on some time horizon, you will be able to produce electricity in America at rates competitive with solar, wind, and gas.
We believe we have the pathway and the line of sight to do that, absolutely. And so part one is the district heating market in Europe. Part two is that same model. You think of the hyperscalers that are focused on accessing power in the United States, the companies that are focused on developing those systems, and we bring the closed loop technology and the applications and the innovation that we have. That combination, we are quite confident over time will become highly competitive in the US market and other markets around the world.
There will be enormous demand for dispatchable power for data centers. Mark, you're a oil and gas guy, came up in oil and gas.
Yeah.
I know that the technology here is similar in many ways. Drilling is drilling. I'm sort of curious, like, how much you think the business model is the same. In other words, like, how much of what you bring from oil and gas is going to be applicable here versus what you're going to have to sort of learn on the fly. Do you know what I mean?
Yeah. And I think it's a great question. I think the fundamentals are very, very similar. At the end of the day, it's about supplying heat and power at pricing that's competitive. How we get there, there's different ways to do it, like fossil fuels or et cetera. But at the end of the day, economics really, really matter. And so first and foremost, those fundamentals of finding the lowest cost of energy supply, lowest cost of heat supply that is competitive in the market. The second is And this is what is highly attractive to me in moving from oil and gas and fossil fuels to geothermal. In regions that are adopting policies, and we see this especially in Europe right now, around aggressive decarbonization,
Sure.
aggressive environmental law, minimization of water use, minimization of land use, geothermal has a place there. This is sort of my own soapbox, if you let me go on that. We talk about wind and solar as, sort of big movers in the renewable space. We often don't talk about the necessity to access critical mineral supplies to manage those developments. We don't often talk about disposal of, the batteries and those same critical minerals on the back end of that. And so on a full cycle basis, as Jeanine talked about, geothermal has the ability to draw from the biggest energy source that's around us, which is the heat of the earth. And the Everloop advancements allow us to do that with no energy input, with no emissions, with no excess water use, and a very small land footprint. And so that's what's attracted me. And again, it all comes back to energy supply around the world is just going to be a basket, right? Some will be coal, some will be nuclear, some will be et cetera, et cetera. Geothermal will play a role there. We just need to get it to that point where it's more visible, it's further down the learning curve, and it's absolutely cost competitive.
Well, let's talk about that then. And maybe, Jeanine, you'll have something to say about this too. I'm curious where you see costs coming down. One of the things when I talked to, Fervo, kind of one of the things they're explicitly trying to do is kind of modularize the process.
Sure.
So there are these sort of repeatable units, and kind of that's how you get on learning curves is with these repeatable units. I'm sort of curious, like where you see advances coming, where you see cost declines and technological advances coming, where you're pushing.
Yeah, it'll come in two areas, and I'll jump in, and then Jeanine, please. The first unconventional well that I drilled 15 years ago took us over 30 days, between 30 and 35 days. As we came down the learning curve, that same well now is 5 to 6 days.
That's shale. That was shale drilling.
It's more of let's call it a siltstone, but similar to a shale, right? There's my geology. That's the full extent of my geology, David. But,
I know. I'm nodding, but I'm secretly Googling.
Googling what it is. I know. But that came from a few things. It came from, sure, practice makes perfect. But as you learn more and more about the rock and the mechanics of the rock and the ability to fully interrelate or correlate that subsurface knowledge, the geology with the engineering into the well design, at the end, in those last wells, there was a continuous feedback loop through artificial intelligence, machine learning, through the flow of information that allowed micro changes all the way through the execution of that well. Let me bring that back to where we are. This is public knowledge, and it's the challenge of a first-of-a-kind project. It took us over 100 days to drill the first lateral.
I read the white paper, and it sounds like some engineers had some bad weeks there. So.
Yeah, well, they had some bad weeks, but as happened, they put their heads together, and the last one was 20 days.
These are the laterals.
These are the laterals.
You're talking about specifically the first lateral took 100 days. The last lateral was
20 days.
20 days. And you think you can keep getting that? I mean, presumably there's a physical limit somewhere, but like how far down could that get?
There is a physical limit, right? But I think that the first and foremost thing that I'll reinforce for people is as we learn, as we just absolutely optimize the drilling programs and the drilling execution, that will come down. And that's been proven across the United States and Canada.
Let me just ask about that. You're far enough down. This was actually a confusion I had. Like, you're far enough down and you're getting into hot enough conditions that it is hotter than what conventional oil and gas drilling equipment is sort of rated for. But you have not developed any new drills. Instead, you're doing this thing where you keep the drill cooler. Can someone explain that very quickly? How are you operating at such depths and in such heat with equipment that's not really rated for that heat?
Go ahead, Jeanine, and then
I'll take that one. Okay, so the oil and gas drilling tools, which allow you to steer and directionally drill and everything, have a limitation of 180 degrees C. Oh, no, what? That is in Fahrenheit. I'm sorry. I should have calculated all that. We'll just talk C. But the reason I bring that up is we want to be able, this is where the next generation geothermal is different from hydrothermal, is we want to be able to steer and do all this directional work that we have done in unconventionals. So you have to adapt those tools and keep them cool to be able to do it. So we actually drilled a groundbreaking, pardon the pun, well in New Mexico in the fourth quarter of 2022. We drilled the world's deepest directional geothermal well on the planet. And we created some new technology, and it's the cooling technology that we drilled there. So we drilled down to 18,000 feet, 450 Fahrenheit, and we take a drill pipe and we put an insulated coating on the outside and an insulated coating on the inside. That means when the mud from the drill rig is cool at the surface, and as you pump it down and it goes through the drill string, it stays cool when it comes out the end of the drill bit deep down underground. And so that is what kept the tools cool while we were drilling and allowed us to steer and do all that work. Once you've built it, though, and you take your tools out, you can operate in that environment. There's no temperature restriction after that. It's just building the system where you have the restriction.
Oh, the initial drilling is the limitation.
Yeah.
And so rather than develop a new kind of drill, you just developed an insulated pipe to keep the drill cool while it's working. And that's going to work all the way down to 5 miles or wherever you're going. You don't
5 miles. And I think, David, when we talk about kind of getting to that point where not only does an Everloop provide all the environmental and sustainability benefits we talked about, it's also your most economic choice for power comes from better efficient execution. But as Jeanine has highlighted, it comes from accessing deeper, hotter horizons because the cost to go down is disproportionately smaller than the gain we get. And that's really our business model is execute flawlessly. Well, how do we execute flawlessly? We go to organizations and companies that are known for that to allow them to do the execution. And then we develop and continue to innovate, which is our strength in terms of how do you access higher thermal delivery. And in doing so, the combination of those two gives us a pretty good line of sight to delivery of power that's highly competitive in regions of the world.
Do you have any kind of specific LCOE target or anything that you're aiming for? Any sort of aspirational price target?
Yeah, of course we do, and I think
that you want to tell us about.
I'm not going to throw this out because then the whole organization will say to me, "How did you give away our internal target?" But I think as any of your listeners could look at what is the current cost of power through SMRs, and I think that's sort of in that 100 range as you come down to wind and solar, LNG. That's right where we need to target. We need to not only be able to say we give you an environmental and stable supply of power, you don't have to pay a premium ultimately to get that. And then those two together create a business model that's highly attractive.
Mark, I've also told the SMR people, when you build a plant and you produce some electrons in exchange for money, you can come on the pod. You'll note they have not been on the pod yet. Since you brought the price of power, one other sort of tech question that I skipped past. The hot water that's brought up is not run through a conventional generator. It's run through what's called an organic Rankine cycle power plant, ORC power plant. Is there anything of note about your ORC power plant, or is it just off the shelf? I mean, is that an area of innovation at all, or is that pretty commoditized at this point?
It's off the shelf technology.
Shelf, yeah.
But there are opportunities. I think a lot of companies are trying to figure out how to make, like most organic Rankine cycle units are boutique in some way, shape, or form. And so that idea of standardizing it, and even something we would like to work on is that you have a power plant and then you operate the subsurface to go with it, basically. So that's like future goals, but basically this is off-the-shelf technology that everyone is using, and it has its own closed loop inside of it. So when you bring up your hot water, it hits a working fluid, has a higher boiling point than the water that you produce, creates a gas. That gas spins the turbine, which creates the electricity. And most, except for like the geysers in Laradello and some of these steam flash ones, most geothermal now is built with that organic binary cycle.
Mark, I'm curious how, or rather, what's the limiter on the speed of scaling? Is it funding? Is it finding partners? Is it finding utilities willing to take a risk on this? Buyers? What are the constraints here for growth?
Yeah, I think there's really two. The primary constraint in the US for us right now is what I would call equivalency, if I can say that. And there's lots of conversations, and I'm sure you've had lots of conversations around where funding is available in the United States, the continued bipartisan support for geothermal, the work around acceleration of permitting and approvals. The closed loop system needs to be included and be part of that. And so, first and foremost, for us, and Jeanine and I had a few great days in Washington last week talking about the success we've had in generating power and the opportunity for closed loop systems to begin to be part of the narrative and the conversation in terms of geothermal development in the United States.
How are they classified now for the purposes of permitting? Like, are they in the same bucket as an oil and gas well, or is there a unique category for a geothermal well, or is there an even uniquer category for your geothermal well? Where does that stand?
Most permitting, like most states that have some form of geothermal, have geothermal regulatory rules. So we just permit it as geothermal well. And some states are more progressive, like Colorado and Texas, which have included deep closed loop systems in the regs. But by and large, I don't think we're going to struggle for permits at all. I mean, other than the same struggles everybody else has with getting permits, the standard struggles. But otherwise, no, like even to the question of how fast can we go, I would say that is an advantage that geothermal has over the SMRs and other nuclear opportunities is we can be built pretty quickly. If the permitting environment is good, end to end, it could be 3.5 years to get your first sort of module in the ground and operating.
Interesting. And how big is the difference if you're doing exclusively heat versus both? Is sticking the power plant on top of it, is that a big chunk of time or money, or like, are you saving a lot by doing heat only systems to begin with?
Heat only is a good opportunity because you're not converting the energy to electricity. When you do that, you only convert and use 10%, but that goes for everyone. So in our case, where we are coming down that learning curve and looking for a good market entry point, like heat does make sense because you can sell, all the heat you're producing and you don't have to build a power plant. But it's still not that big of a cost. You save some cost on the power plant, but like I said, 80% of the cost is drilling, but it's this energy sales on you're selling most of the energy you're producing. So it is a good sort of beachhead, market entry strategy if you want to maximize the economic opportunity.
I would add to that. I think back to that question, David, you asked about sort of what are those constraints. I continue to call for policymakers around the world, Canada, the United States, and otherwise, to recognize that geothermal has a role. And it's important. It should be supported.
It seems like you're pushing on an open door. Like, yeah. I mean, I don't know what experience you've had, but it seems like that word is, at least in my circles, like that word is out.
Yep.
Everybody's excited. I keep talking to legislators who are excited about it. I wonder if you find that like you are getting a welcome reception.
I think it's changing. For sure, it's changing and it's improving. Probably better in the U.S. than our home country here in Canada, for sure.
Huh. I wonder, it's like the birthplace of drilling.
Alberta.
I know. That's like drilling central.
This would be a whole different podcast that could go on for hours and hours and hours on this one. But and then the second is the opportunity to identify these regional partners, to look at those that share the same view of how to progress the development. And we'll continue to innovate. We'll continue to drill deeper. We'll continue to access higher thermal output, and all those together will get us there. It takes capital, it takes time, but pretty confident.
It also presumably takes some policies. How do you see the current policy landscape, and is there a particular policy lever that would help you? Is there a particular thing you're pushing for? It seems like most of the IRA got wiped out, but it kind of seems like the geothermal bits survived in the wreckage. I'm not totally sure how that played out. So what's the policy landscape look like?
Well, I'd love to just roll back to the IRA for a moment. Geothermal is actually the only renewable that got zero in the IRA. So
no kidding.
In some ways, the fact that IRA got rolled back didn't affect us because we got zero. We really got zero out of that. So that was like a miss. I think maybe, I don't know how we missed it, but it was a miss. What I think was preserved in the new One Big Beautiful Bill is the preservation of the tech neutral tax credits and geothermal and nuclear, have the ability to have access to these investment and production tax credits, which is a good policy. If you're more of a larger company and you have a lot of revenue and you're building projects all over the world, it's a bit easier to take advantage of that. When you're a startup, I like to think we're in scale up mode now, but you have capital constraints. And so there are other financial instruments that help companies that are at the stage that we're at. And I think those sort of grant, non-dilutive sort of grant opportunities or milestone-based grant opportunities.
Wasn't the LPO, wasn't the Loans Programs Office supposed to be in that business? Did you have dealings with them before they, I believe, also kind of got wiped out?
Yeah, the LPO was real. They are really great there. They are looking to support any project. At least when we were working with them a few years ago, you had to have a stake in the ground and build one in the US first, and then you could get access to the low interest debt. So I think that may be changing now. I think there's certainly opportunities on that side. So I think that is a thread that we'll absolutely continue to pull on. And then, of course, we're supportive of all the permitting reform because what our investors need is certainty and market signal that this sector is investable. So when you start seeing things like preservation of the tax credits, different low interest debt opportunities, grants, just all these in conjunction send a market signal to, say, for example, the hyperscalers who right now, like we do have to come down this learning curve. They're a consumer that is willing to pay. And we've seen this with this 3 Mile Island coming back online, right? And there's a power purchase agreement with one of the hyperscalers.
They are willing to pay.
So they're willing to support that coming down the learning curve. So they're an important voice in the conversation. And so how can we work on a public-private partnership space that shows them that, yes, there is some public interest and investment here. So we're going to have the company showing up, we're going to have the partner showing up, but then we also have some public investment from the government. So that's how I describe it.
I wonder if it's part of your strategy going forward here to target like these hyperscalers, as you say, need a lot of power and need it quickly and have a lot of money. And that makes them targets for a lot of people's interest, including yours. I wonder if there's like a Google or somebody out there who would be willing to pay more for those first few of your plants just to get it ramped up so they can use it. I'm sure, Mark, you
might be thinking about that.
Talking with people.
Yeah, and I think everybody can kind of put the intersection together of where the opportunities are. And we'll look forward to coming back at some future podcast and talk about where those opportunities landed.
Yeah, I would love to find out. Okay, final question. Mark, when I talked to Carlos, the CEO of Quays, he has grand designs. He basically wants to talk the global oil and gas industry into doing geothermal instead of oil and gas. He's got stars in his eyes. I wonder, like, is the long-term goal here to get bought by an oil and gas major and start kind of trying to change that industry from the inside out? Do you see that as a plausible route here? I'm just curious about the long-term relationship between oil and gas and geothermal.
I think we're very different industries. Like, I believe there's room go forward for multiple players in the mix as it relates to energy supply around the globe. You know, I've had the great pleasure of leading the global upstream business for a major international oil company, and regions are different. Supply basins are different. Costs are different. And the way we think of Eavor is we have an opportunity to provide energy and heat, power and heat, in a manner that's going to be cost competitive in many, many regions. Some we won't be, and brings environmental and social benefits. But I'm a big believer that the energy mix will change, but there is a role for just about every type of energy go forward, especially as global populations grow, as energy security begins to become more and more paramount, especially, for example, in the United States and Canada. And as we see an advancement of regions around the world that live in abject poverty, they need low-cost energy to move from poverty. And so I've never been a believer personally that solar will replace coal and geothermal will replace oil, and the geothermal industry has an opportunity to contribute to that mix. The proportion of that mix that geothermal achieves will be cost-based. It will be how competitive we are economically. That's our focus.
All right. Well, that's a good way to wrap up. I guess we'll have you on in a couple of years and see.
Couple of years? Come on.
well, we'll see. We'll see what you do.
No, I appreciate it.
I'll have to set a new aspirational target for you, Jeanine, for you to come back on the pod to give you something to work for. All right, you two. Thank you so much. This is fascinating. I've been, as I said in the intro, I've been wanting to do this for a long, long time. So I'm so glad you guys pushed through and it is working out. So thanks for coming on.
Thank you for taking the time and having us.
Thank you for having us.
Thank you for listening to Volts. It takes a village to make this podcast work. Shout out especially to my super producer, Kyle McDonald, who makes me and my guests sound smart every week. And it is all supported entirely by listeners like you. So if you value conversations like this, please consider joining our community of paid subscribers at volts.wtf, or leaving a nice review, or telling a friend about Volts, or all three. Thanks so much, and I'll see you next time.